Okay, so now you had a chance to train a model on this data set. And in this tutorial, we're going to think about how to best evaluate that model so that we know that it will work well for our purposes in the real world. So in this tutorial, we're going to learn about the concepts of generalization and overfitting and how they relate to each other. And we're going to learn about splitting our data into training and test sets and why it's important to do that. So the model that you trained, it looks like it's performing well, right? So we have on the x-axis here predicted temperatures, on the y-axis we have the true temperatures, and so if the model were performing perfectly, all the points would fall on this red line, but they're pretty close. So the model seems to be performing well. In addition, we know that the R squared value was large for these random forest models that were trained to predict temperature. So it looks like it's performing great, which is kind of surprising, right? Because this is actually a pretty difficult problem, this idea of building a climate model emulator. So is this really the right way to evaluate the performance of our model by figuring out the R squared value on the data that we train the model on? Well, it turns out that testing a model's performance is actually somewhat complicated, and you need to think about some things when you do that. But when you train a model on data, you have to think about what data you should use to evaluate that model. So the performance of the model on the exact data points that it was trained on tells us something about what the model was able to learn, but this can't be the full picture. We also need to evaluate the model on data points that it wasn't trained on, but which represent the same kind of problem that we expect this model to solve. Because when you go to deploy this model in the real world, you're not going to just give it the data points that it was trained on because we already know what the predicted temperature in 2050 is for those data points. We had the answers already. That's how we trained the model. So when we go to use the model for real, we're actually going to give it points that it wasn't trained on. And so how do we know that it will perform as well on those points? When you evaluate a model on data that it wasn't trained on, it lets you measure how well the model generalizes, meaning does the performance that it gets on the exact data points it was trained on, does the model generalize and have that good performance for data points that it wasn't trained on? If a model does really well on the data points it was trained on, but doesn't do well on new data points, then we call that model overfit. We say the model has overfit to the training data. So let's think about this concept of fit. Basically, the idea of fit is a relationship between the complexity of the model and the patterns that it needs to fit in the data. So if we think of a situation where we have data points here that mainly follow this kind of curve here, like a quadratic function, but we try to fit that model with a line. We use linear regression to try to fit a model to that data. Then we're going to end up with a model that is underfit to the data. The model just doesn't have the complexity in it. It doesn't have enough free parameters to be able to fit the true nature of this data. Now, let's say we use a quadratic model or some other kind of nonlinear model. Now we have a model that can produce a prediction line here that has a shape that really matches the shape that we can see by just looking at the data. We can kind of see this looks a little bit more like a quadratic function with some noise on it, right? So this would be a model that is fitting the data well because it's capturing the true complexity of the underlying function that the data represents. Now, if we continue and we build a model that has a lot of free parameters and can create all these kind of wiggles and nonlinearities in its predictions, then that model might come to fit all the individual data points, but in doing so, it's actually not capturing the function that the data really represents because it's fitting to all these noisy bits where we don't really want it to do so well on every single data point it was trained on. Instead, we wanted to do this middle thing where it's capturing the general trends, and therefore it's capturing the underlying function that's creating this data, and it should do well when we test it on new data that it wasn't trained on. So we want to get models where the complexity of the model matches the complexity of the data, and therefore the model and the data are a good fit, and the model should perform well on data points that aren't the exact ones that it was trained on. So overfitting is a consequence of working with very flexible models, which all these modern machine learning models are. They usually have a lot of free parameters, so you need to make sure that you're doing things to make sure that you're not overfitting your model to your training data. So in that way, it can be controlled by varying hyperparameters, like we talked about before, the depth of the decision trees, that kind of thing, the number of trees in the random forest. And if you do have a model that's overfitting, it will cause poor generalization performance on held out data. So you'll have a data set that you'll evaluate your model on, and you'll see that it didn't do well on that data set that it wasn't trained on. So in this way, we measure overfitting by taking our full data set, splitting it into a training set and a test set. Usually the training set is about 80% of the data, and then you have this held out 20% that we call the test set. So then when you go to train the model, you only use the training data. You only use that 80% to train the model on, and then you evaluate the model on both the training data and the test data and see if it's performing way better on the training data than it is on the test data. And then you might have a model that was overfit. So now you're going to go explore this in your own models.